And just to remind you, this was like the slide from last time. Okay, so you have your base and your exponent, and then your answer. But your answer now becomes your input, and the new answer out of a logarithm is actually the exponent that you had. So an example of that was 3 to the power of 4 is 81, which implies the statement that the log base 3 of 81 is 4 because the exponent on 3 of 4 gives you 81. You can always use this strategy to kind of like get yourself thinking about what it means by rewriting a log statement as an exponential statement on the side. So like if you're asked to find log base 3 of 81, I could rewrite this and say, well, if it was x or y or z or whatever, m, let's say just for a different letter, then I know that 3 base to the power of m, power is the answer, is 81. And then I can think, well, 3 to the power of what is 81? Well, I know 3 to the power of 4 is 81. So it's kind of like a guess and check to confirm that it's a 4. And clearly, if we can write this as a base to a power, then we know that the m has to be 4 because the exponents on the same base must be the same, right? So that is actually a theorem, but I mean, we can take that for granted. Like if we have the same base, we have the exponents must be equal to themselves. And this is going to be useful when we start solving the equations that have an x value in an exponent or in a logarithm. But we'll get there in a bit. Let's just, first we need some properties because sometimes they're way more complicated than just like one thing. And so, for instance, if we had log base 3 of 2 times 81, which is 162, there's a way for us to break that down so that we can still calculate some of it more easily than other parts, because 162 is not a nice power of base 3, right? So we need other tools to work with things that don't work out as nicely as something like this. So that's the motivation for talking about different properties. So just to review, some of the properties we addressed last time was anytime you have a log of any base of 1, you always get 0. Now, why is that? Well, you can convince yourself by converting it to exponential form. So just try that. Think about what you would do. You take the base to the power of the exponent equals the inside of the logarithm. Anything to the power of 0 is always 1. And same thing, if you rewrite this one, you're going to see base to the power of 1 is b. Yes, that has to be true because b equals b, right? But what that does is these are not always given. So if you just have like, okay, evaluate log 7 of 1. Well, right away, you know that's a 0 because of this property. Or if you see log base 7 of 7, you should know that that's a 1 just because of this property. So that helps with simplification sometimes. We also learned that because they're inverses, if you put one into the other, you should still get x. And we talked about, okay, if you check that, b to the power of x is b to the x, yes. And if we rewrite this as the base b of x, the answer is the exponent, then, you know, these are kind of redundant. They seem obvious, but they're very useful. These are particularly useful when we start doing equations. So like if you ended up having to solve something like 7 to the power of 2 equals x, so x should be 49, we could actually take both sides as a power of 7, which actually we're applying the inverse to both sides. We're allowed to do that because we knew before that the exponents had to be the same. If you had, remember the example was if you have 3 to the m equals 3 to the whatever 4, then that means m has to be 4. And so if you can reverse that statement, So you can apply the same base to both sides. And this kind of like cancels it out because of it being an inverse. And on the other side, you have 7 squared. So x should be 7 squared, which means x is 49, which we knew log base 7 of 49 should be 2 because 7 to the power of 2 is 49. But before we can get to like more of these solving equations, we still need to come to some of the other properties that help us manage bigger statements. So we need to come to some of the operations because, you know, with algebra, if you're trying to solve an equation, sometimes you have more sort of operations going on, like you have a plus, you have a bracket, you have like things you have to simplify before you can say subtract 2 from both sides or square both sides or whatever, right? Before you apply any sort of inverse, sometimes you have to simplify. And so we need to learn how to operate or simplify logarithmic expressions so that when we have an equation, we can simplify it and then apply the inverse. That's kind of our goal here. Okay, so there's a few different properties, and they're related to the exponent properties. So when you had exponent properties such as b to the 2 to the 3, and you knew that that was b to the 2 times 3, or you knew that b to the 2 times b to the 3 is b to the 2 plus 3, those were exponent properties. And so because logarithms are the opposite of exponents, we're going to base our properties on the ones we know for exponents. So we're going to build to, I'll have a summary of like all the different laws, but like let's just take a look at the exponent laws first, the ones you already know, and then we'll convert them into logarithm laws. So the first one, the first one that comes to mind is if we multiply two exponents with the same base, what happens to the actual exponents? Yeah, m plus n, right? Nice. You add these together, right? So we know that, we don't have to reprove that. But now, how does this inform our process? Well, you can loosely think of it as a multiplication of the sort of answers is giving us an addition in the exponents. And since logarithms answers are exponents, it's almost like that multiplication is going to become an addition. That's our intuition here, but let's like see it through. So I'm going to call this part big M. So b to the little m is equal to big M. Let's say that's n. So b to the little n is n. And so like if I know that orange one, the b to the n is n, then I can reverse that and say that log base b of big N is little n, right? And that's just the definition of a log and the transformation of that statement there. And again, the log base b of big M is little m. Remember, the answers of the log are always the exponent that was there before, right? Okay, so the reason why I did that is so that I can see what happens if I had this to start with instead of these to start with. So I'm just going to rewrite what I have here in black. I'm just going to rewrite this part as if this was m times n, because I've defined those here. And that equals b to the m plus n. And now I'm going to take this statement and transform it into its log form. So think with me here. How would you convert that into its log form? Well, you always think the b is the base of the log. So that's going to go into the base of the log, right? Of the logarithm of something is equal to the exponent. And it's always of the answer. So I've just rewritten it as its log form. So I'm essentially taking the exponent law and rewriting it in log form. Okay, so we're almost there. Now, if I go back and consider what m was log base b of m, and n was log base b of n. So if I just put those in, then I get this, log base b of m times n is equal to m, which was the same as log base b of m in log form, and log base b of n in log form. This is actually called my product rule because it's coming from this was the product rule. So this is also my product rule. And it tells me that inside the log, if I have a product, it will split as an addition of logs. So now what you're going to use that for is you're going to be able to go back and forth. If you see an addition of logs, you can always compose it as a multiplication of those things in that log. If you see a multiplication that you want to expand, you can expand it. That's helpful when you want to calculate things that don't like simplify nicely, and sometimes there's an x and a number, so then you'll be able to split them up. I'll give you a few examples in a second here. But the other important thing here to really emphasize is there's a very common error that happens, and a lot of times that where the multiplication and addition is gets mixed up. So you'll see like log b of m plus n, and you'll try to expand that, and you'll just try to like distribute that log m plus log n. That does not work because it has to be a multiplication in order for it to become an addition. An addition of those two things won't work because we don't actually have a rule for when you're adding the two bases with the same exponent. Right? We don't have a rule for b to the m plus b to the n. So we can't just distribute. There's no distribution, like get rid of the idea of distribution from your mind when you're working with logs, right? Yeah, like we don't know what that is. We just have to leave it as is. So just be really careful. Multiplication inside becomes an addition outside. So here it is, product rule, multiplication inside. And so we can try a couple examples. So if we had this, how can we expand that, right? Well, we can expand that as log base 10. If it's not written, it's a 10 of 10 to the 3 plus log base 10 to the 2. So I can make that multiplication into an addition of the same log base. And we can check this actually. The reason why I chose this example is because you can check this easily on a calculator log or even in your head, because log base 10 of 10 to the 5 should be the same as this one plus this one. So think about what log base 10 to the 3 would be. It's asking you essentially, what exponent do you put on 10, base 10, to get 10 to the 3? What should that be? Okay, rewrite it again. So log base 10, because if there's no base written, it's a 10, of 10 to the 3. Let's say that equals v for value. Rewrite this in exponent form and tell me what you think v should be. So 10 to the power of v should be 10 to the power of 3. So what's v? Okay, you get 3. Why do you get 3? It is the exponent, right? The exponent on 10 of 3 gives me 1,000, which is 10 to the 3. It's literally asking you what is the exponent on this base that gives me this answer. That's what a log is. It's the reverse. It's kind of, you have to trick your brain to think of the reverse of, okay, if I want the answer to this, it is asking me what is the exponent on this base that gives me this, right? V has to be 3 because the only way to get 10 to the power of 3 from 10 to the power of something is to have that something be a 3, right? So what should log of 10 to the 5 be? Right, this should be 5, shouldn't it? And again, do you remember that law where it was like the same base technically just cancels out? Because if it's the same base, it's basically like you're taking the log base 10 is the inverse of 10 to the 5. So we're only left with a 5 because it's literally the inverse of that. So, okay, so this is supposed to be 3. And what's log of 10 to the power of 2 supposed to be? 2. Yeah. Okay, and does it check out? Is 5 equal to 3 plus 2? Yes, right? Right. So let's see, another example would be like if I had log base 10, so I won't write it, of 10x. So that is 10 times x. So because it's 10 times x, I can expand it as log of 10 plus log of x. So then I can simplify this part because what's log of 10? What exponent on 10 gives you 10? So it's kind of like there's a power there and this kind of cancels out and I got a 1. And I couldn't do anything with that because that was a log of x. So I have to leave that. So it's just, this is the simplified sort of like expanded form, and this is sort of the, this is condensed form. So they might ask you to expand, they might ask you to condense, and we need to look at some of the other sort of log laws, which are parallel to the exponent laws. Okay, so the same thing, remember what we did with division? Like if you had b to the x over b to the y, you would go b to the x minus y. So that relationship is also going to be mirrored there, just like we did with the previous one. So just to redo that example, so if you had b to the m over b to the n, that would equal b to the m minus n, right? And if I call this m, then I can rewrite that as the log form of it. Log base b of m is little m, and the other one, n. Log base b of n is little n. So if I just do that, then I have m over n equals b to the m minus n. Now if I rewrite this one as its log form, it's log base b of m over n is the exponent only, which is then going to give us, so this is the same, pretty much the same kind of sort of proof. So your concern is mostly, first of all, understanding how this happens. So, you know, you might be asked to kind of like, okay, why does this work? You can always look this up here. But the biggest thing that you're going to use this for is when you see something that's like log of 10 to the 5 over 10 to the 2, I mean, that's easy enough to simplify and say that that's going to be log of 10 to the 5 minus 2, which is 3, right? But you could also separate the log and it should also work. That's log 10 to the 5 minus log 10 to the 2, right? So this is 3, this is 5, and this is minus 2. Yeah, 5 minus 2 is 3, right? I'm using tens just because they're the same base. The same thing would happen if I used like log base 3 and then I used a 3 to the power of something. The base doesn't really matter too much. I'm just using tens because they're easier to consider. Okay, so far we have two laws. We have the product rule and the quotient rule. So multiplication inside is an addition outside. Division inside is the subtraction outside. And there's a couple more. So one would happen if you started having more things multiplied together. I'm just going to reuse that product rule, and the more things are just going to become more of those pluses. So you could have m, like 5 of them, and then you'd have 5 of the same thing written out, added together, right? And that's coming from the product rule, but we just do it again and again. So what that tells us is that I could actually, instead of saying I have log b of m plus log b of m plus log b of m, I know that's going to be that many of them. This is one of these plus one of these plus one of these. It's 3 of these because they're the same ending. And so this tells us is that if you have an exponent inside the log, you can always kind of like drop that exponent down outside and it will be the equivalent statement. And that actually comes from the product rule happening over and over again. So let's try an example with base 10. So log base 10 of 10 to the 5. I mean, you should know that this is 5 now based on our previous conversation. But if you use this power rule, that would mean that the 5 could also just come up front, 5 log 10. And let's see, well, log 10 is 1, because the exponent on 10 to make 10 is 1. 5 times 1 is 5, so it works. Right? So you could either evaluate this by just asking yourself what power of 10 gives me 10 to the 5, or I could drop that exponent to the front of the log as a multiplication. It kind of like comes out, and then it gives us that. So that's the power rule written down more formally here. So that exponent there drops down up front and it's equivalent. So you could go back and forth between these. So to take stock, this is what we have so far. Okay, so you have that. Multiplication becomes addition. Division becomes subtraction. And repeated multiplication becomes obviously just like a repeated version of the product rule. Those will carry us a lot of the way. We pretty much only have like one left, but we're gonna let's just use these a little bit to see how they work. Notice that you do not have a rule for log base b of m plus n. Like there's no rule for that. You cannot make that log b of m plus log b of n. It's a very common thing to just think, oh, I'll just distribute this log. It doesn't work that way because the exponent rules don't work, as I mentioned before. And we also don't have a log base b of an m minus n either. So we don't have any rule for minusing or adding inside the log to expand it. We just have to keep it as is. We do have rules for multiplying, dividing, and exponents. Okay, so this is like a summary of all the properties that you can use. You can like refer to this. It's from the textbook. We've done this one, we've done this one, we've done this one, we've done this one. And then these were the ones we just talked about. This is like, I already talked about this, like basically if you have the same thing on both sides with a log, that's the same. It's just implying. So I can apply a log on both sides, or I can apply an exponent on both sides. These are kind of like redundant. They're kind of almost too obvious. So I would really focus on these properties here for yourself. And that's going to work in questions like, and this is again leading up to being able to solve questions, but before we can solve, we need to learn how to simplify, because it'd be really hard to deal with this the way it is right now. But sometimes if you expand it, it can help you see a different way of simplifying something. So let's try to expand this. Okay, so which rules can we use here? Which of these three rules are we using? Product, quotient, power in here. Okay, yeah, we have a quotient rule. We also have the product rule up top. So you can, I would say because the quotient is kind of overbearing, like we have 3x over 4, I would do that one first. I think you have good intuition there. And then we can fix the product as well. So right now, if I treat this as 3x over 4, I can just, and because it's log 10, we usually don't even write it. For the base of 10, it's just log. So log 3x minus log 4. Right? Do you see how that division became a subtraction? Okay. We're not done yet expanding because there's still a multiplication. If there was an addition or subtraction, we couldn't do anything more inside. But because there's a multiplication, that can be log 3 plus log x minus log 4. And that's as good as we could get. Sometimes these will simplify because there'll be special powers or something, but there's nothing really to do there. If we had an exponent, like if you had an x squared, then you could drop that 2 up front, but nothing else would happen. If a log does not simplify nicely, then you just leave it. It's kind of like when you left root 5, instead of making it a decimal, you kept it in exact form, exact values. The same applies in logs. You would want the log 3 or log 4 to just be written as an expression, like perhaps you'd put the x term first. And you would just let someone figure out what that is based on the accuracy they need. So if they want exact values, you want to leave it as like just like that. If you wanted to estimate it, you could just use the calculator and see what it is, but you'll have decimals because 10 to the power of what gives you 3? Well, that'll be probably some sort of negative and decimal because it'll be a fraction, I think, yeah. Okay, so why don't you just take a minute and try some of these. Notice this is log base 5, but really that just means you need to include log base 5 for every time you expand. So try this one first. Maybe just take a minute or so on your paper and see if you can use the product and quotient and power rule on that to expand it. If you're done, you can try this one. It's a little more complex. You have to see the root as a power of a half. Oh, I don't know. Somehow that was missing. I think, yeah, it needs a log. So 1 sec, I'll rewrite that. I'm going to do ln. Ln is the same as log base e. Awesome. Yeah, so it's going to be the product, log base 5 x, and then log base 5 y squared, and that square is going to come down. And then you're done. That's it. I mean, we're building into an equation, and that's when you'll have to do a little more, but at this point, that's all we can do for expand. And then the next one, if it's ln, and again, I would do the outside sort of bigger thing first. You can do them all at once if you want. Ln again is log base e. So now once I split this ln e plus ln root y minus ln z cubed. Ln e, because this is the same base of the same base, it's going to be a 1 because e to the power of 1 is e. Now y is y to the root y is y to the half, so this will be plus 1/2 ln y, and this will be 3 ln z. That one's a little more tricky, so I just wanted to show you a more complex example as well. So if you have a root, you use the exponent form of its fractional exponent form and then drop that down. If it's just an exponent, that's coming down as well. And if something can simplify, then you simplify it. Okay, so the other way, the other direction is of course the other way. So you'd be given this and asked to combine it to a single log. And sometimes that's a useful strategy to use when you're solving these equations. So let's see if you can try to condense this back to what it would have been before it was expanded. So somebody's expanded it. How do you condense that? You have that half there that's going to come back into it as an exponent. That 2 is going to come back as an exponent. Once you combine that, then you want to think of that overall addition is going to actually mean a multiplication inside the ln. Okay, so that 2 becomes x squared, and that, right, that addition inside can't do anything, but that half can go back as an exponent. So that was the power law. We also know that the exponent of a half is a square root. And then we also know that the plus is a times when you combine it together. So I know this is a bit complicated, but hopefully you can see that structure kind of coming back together. You can always practice expanding it and see if it gives you that back again. And you're just in your mind going to have to replace, when you see ln, it's basically like an log. Like log is the same as ln, it's just a special base. Okay, so here's another one, simplify, condense. I mean, you see that this is added. So these two, like that'll come back up as an exponent. They're all log base 5, and these are going to be multiplied together, and then that's going to divide there. And because some of this can get simplified, like factoring sometimes ends up happening in here, right? X minus 2 squared is 2 of those, and x squared minus 4 factors to x minus 2, sorry, x minus 2, x plus 2. And because these are the same, so that then simplifies to log base 5 y x plus 2 over x minus 2. I mean, typically you don't get ones that are this long, but just for the, you know, almost for some mathematical entertainment, that's what would happen there. And there's one more rule that helps us evaluate things that have a different base and then they have a number. If you want to estimate the decimal of it, there's a way. And I told you about this last time, but I didn't show you why it works. So I told you that, like, what if you had to evaluate this and you didn't want to keep it as a log base 3? You wanted to put it in your calculator and figure out what the decimal approximation of that value is. And I had told you you would do log base 10 of 2 over log base 10 of 3 to calculate it. Once you do that, log 2 divided by log 3 on your calculator, you'll have an approximation decimal, whatever that is. So that's called the change of base formula. So I just want to show you how that works. So let's just start with what we have, log base b of x in general. I'm going to rewrite that as its exponential form. So b to the power of y is x. Now, what I can do here is I could take the log of both sides. I'm allowed to take any base. So because we're doing the change of base, we want to do a different base. Let's say c, log base c of both sides. Otherwise, I'd just come back to the start. Nothing would have happened. Okay, so I take base c of both sides. Now, if I apply that law, the power law, the y comes back out. I have log base c of b equals log base c of x. And then if I get y by itself, I just want to prove to you that this is true. If I divide both sides by log c of b, then I get my change of base formula, which is essentially like if I wanted it to be 10, because that allows me to evaluate it through a calculator, then I'm taking kind of like log of the top over log of the bottom, kind of, right? Log of the top of x over log of the base. So that's the change of base formula right there. So that is why I can do this as log base 10 of 2 over log base 10 of 3. Okay. Or I could have done ln of 2 over ln of 3, as long as it's the same base on top and bottom, and then I have the main number over the bottom number. That helps me convert it if I need to convert it to a different base. This is just the formal presentation of what I just said. So I'll just leave that in there in case anybody wants to take a look. Okay, so if you wanted to evaluate each logarithm and round it to the nearest 10,000th, like if you really wanted the decimal form of these exact forms, you need to know how to access this on your calculator. So you would take your calculator. So if you can grab your calculator, and the change of base formula would tell you that instead of log base 3 of 18, which you can't actually enter into your calculator, you can do log of 10 of or ln of 18 over log or ln of 3. You have a log button, you have a ln button, but you don't have log base b necessarily. I think you might actually have it under like special functions, but it's easier to just do this than to go into that. I just have to warn you about something. Because of the way you would type it into your calculator, you have to be really careful about the brackets. Because if your calculator is going to open a bracket here, if you go 18, and then if you just type the division button right there, it's going to put that next division thing into that bracket. So you have to close the bracket and then divide by log of 3 close bracket, if that makes sense. So let me know if you've got a decimal approximation of that. 2.6309, and nice you caught that there. Okay, cool. And same thing for that, you're going to go log 400 divided by log 12, or ln 400 over ln 12. It should give you the same thing. So there's a whole bunch of applications. Generally, like when you see the Richter scale, that is actually a logarithmic measure. The Richter scale is actually a measure of like every point on the Richter scale goes up by a power of 10, right? So 10 and then 100 and 1,000, 10,000, and so on. And so 5.9 on the Richter scale is not a linear kind of growth representation. It's an exponential type growth. And so to get that back again, you need a logarithm. And so just out of an interest, like they developed the Richter scale to represent the ratio of intensity. So the intensity of the earthquake as compared to a 0 level earthquake. So the amount of like shaking they see on their little measuring charts would be like the 0 level, and then the number of times that this new earthquake scenario has been in compared to the regular base scenario is the measure of intensity. So we rewrite that as its exponential form. Log is base 10. So 10 to the power of m, which is the measure of magnitude of the earthquake, is equal to this intensity ratio. So that's what that means, is that when you hear that it's like a 5.9 or a 3.2 or a 8.9, that is the exponent on 10 that represents how many times more intense this earthquake was than regular baseline level, 0 level. So just to give you an example of that, like if you saw April 2012 Oregon earthquake measured 5.9 as the magnitude. So the magnitude is 5.9. So that means 10 to the power of 5.9 was this ratio of intensity to the regular earthquake. So if you look at that, 10 to the power of 5.9 on a calculator is quite a big number. And so it's that many times more movement in the earth than that of no movement in the earth. That's what that means, if you've ever wondered. And so, yeah, if there was a magnitude 9.5 and a magnitude 7.1, if you wanted to compare how much bigger one of those was to the other, right? The Chile earthquake is 10 to the 9.5 in its intensity, and the San Fran earthquake is 10 to the 7.1 intensity. And because they're saying compare the intensities, a comparison would involve like looking at how much bigger is this one than this one. So you would divide it as a fraction. You'd say 10 to the 9.5 minus 7.1, and then you'd get your 10 to the whatever that is as a decimal sort of approximation would be representative of how much stronger Chile's earthquake was than San Francisco's earthquake. Okay, so they also use this to actually, so how they get that magnitude is from the actual seismogram. And they'll have like that first wave and they'll like look at that time. And then the S wave is, which is like the big sort of bang, and the amplitude of that, of how far that goes out. And then they basically have a formula that involves logarithms to calculate that. So if you wanted to identify this was our wave on our seismogram, you would drop that information into the formula and calculate it. I'm just showing you where logs, anytime you have an exponential sort of situation, it's going to be there. So you would basically put that in and say log of 23 plus 3 log of 8 times 24, and then minus 2.92. That's the formula they've developed. That's what they would use to identify what the magnitude is. And so knowing how to get this in a calculator, you just really would type this all in, would help you out. Another situation where it's times 10 times 10 or divide by 10 to get through between the things is pH. pH is a scale that is also like this. The pH values are actually the exponents of 10 on this scale. We won't really go into this one right now, but I have included some examples for you to look at. It's again just the exponent. I'm not really going to focus much on that, but I'd like you to know that pH scales are exponential, therefore logarithmic.